Welcome to section 2.7b, graphs of rational functions. This is a continuation of the last section. So we're going to be doing things like graphing things by hand, just like we did in the previous one. But first thing I have this one up here, it says graph f of x, and this is the function on your calculator. So this is what I graphed. And when you look at it, you'll notice that there's a vertical asymptote, it looks like, at 2. But you'll notice that in the graph it looks continuous over in the negatives. And the question is, what do you notice about x at 0? So in order to do this, if you don't graph this function on your graphing calculator, this is what the table looks like. And you'll notice that at x equals 0, something else is happening. In the previous section we talked about vertical asymptotes, horizontal asymptotes, and so in this one, something else that doesn't have an asymptote at x equals 0, but something else is going on there. There's an error. It doesn't exist at 0. And you could see it by if I did plugged in 0 into this function, I would end up with 0 on the bottom. And so there's a problem. And if you guys remember from Algebra 2 class, when you have this error and there's no vertical asymptote, this is where a hole in the graph will appear. So today we're going to have graphs that are not only going to have vertical asymptotes and horizontal asymptotes, but holes will start appearing in the graphs also. So this first function here, we're going to go through and get as much information about it as we possibly can before we go ahead and graph it. I'm going to first find out the horizontal asymptote. And the reason I'm finding the horizontal asymptote is because I've noticed that the degree of these guys are the same, so it's the leading coefficients again, and so for my horizontal asymptote I could say that y is equal to 1. So I'm going to have a horizontal line on my graph where that I'm not going to cross, and it would be something like y equals 1. So there's my horizontal line. And so then let's look for vertical asymptotes. Well, vertical asymptotes would be setting the bottom equal to 0, but I got to be careful that there aren't any common factors, because remember, that's how we get holes in the graph. If you remember from years past, if I go ahead and factor the top and the bottom, I can see if there's going to be any holes. And so on top I have 12, I'm multiplying to get 12, and I'm adding and subtracting to get -7. So that would mean the only way I could get that is if I had -3 and -4. So my top factors to x minus 3 times x minus 4. On the bottom down here I have -8 and -2, so I'm looking for the factors that give me -8 that multiply together to give me -8, so one positive, one negative, and will combine to get me -2. So the way to do that would be like -4 and +2 would get me -8 when multiplied, but when added would get me -2. So on the bottom I'm going to have x minus 4 times x plus 2. And so with this factoring, you'll notice that x minus 4 is in common, so it is not going to be a vertical asymptote. They basically would cancel out to get rid of that. And so we have a function that agrees everywhere, but at x equals 4, this function right here, x minus 3 over x plus 2, this function is exactly the same thing as the original function, except for at x equals 4, where the hole is, where the hole in the graph is, where we say x minus 4 equals 0, which is x equals 4, where the hole in the graph is, this will fill it in because it doesn't have that specific spot in it. So at x equals 4, somewhere out here, whether it be above or below, when I draw in my graph, I am going to end up having a hole in that spot. So we just got to remember that. Also in this case, so now to find the vertical asymptote, I'm not going to set the original bottom equal to 0. I'm going to set x plus 2 equal to 0, and that will give me that x equals -2 for a horizontal asymptote, for a vertical asymptote. So at -2, I'm going to get a line that looks like this. And there's my vertical asymptote. So I've got a vertical asymptote, I've got my horizontal asymptote, I know there's going to be a hole at 4, and so now it's just a matter of figuring out what's going on for the rest of the graph. And so I've got to pick a few points to do this. And so to pick my few points, let's see, alright, I'm going to pick, I always go to the left and the right of my vertical asymptote. So the first one I'm going to pick, let's see, let's go with setting up my table, x and y. I'm going to pick, let's go with -3 and -4. -3, -4. And then for my other side, I'm going to pick something like, I'm going to go kind of over here, because remember we have a hole at 4. So I'm going to see what's happening around there. So I'm going to say, let's pick x at 3 and exit 5 and just see what's going on. Although 0 would probably be a good information. It would be a quick little information. And remember I said that the graph is going to agree at this function exactly the same as the function up here. But I'm going to use the whole thing here just as use the whole function just to show you. I could use a shortcut and use this function for these guys over here, but I'm not going to. So I'm going to plug in these guys into my function. And so plugging in -3, I get -3 minus 3 times -3 minus 4 all over -3 minus 4 times -3 plus 2. -3 plus 2. So I just kind of did the work. I wrote out the work there. And so it looks like I'm going to get -6 times -7 on top, which would be positive 42. And then on the bottom, I'm going to get -7 times -1, which would be positive 1. And so, or positive 7. -7 times -1 is positive 7. So 42 divided by 7 means that the value I get at -3 would be positive 6. So 1, 2, 3, 4, 5, somewhere up here. So I'm guessing the graph is going to kind of go like this, but we'll find out when we put in -4 to see what happens for this graph. And so by doing that, let's see, if I put in -4, I get -4 minus 3 and -4 minus 4 all over -4 minus 4 times -4 plus 2. So simplifying this, I get -7 times -8, which would be 56, and then -8 times -2, which is -16. So it looks like I'm going to get 7 halves for that one, which is, so at -4, so 7 halves is 3.5, so 1, 2, 3.5. So my graph is going to do something like that. And so that's what the graph looks like for that part. And then now I'm going to do the same thing with 3. I'm going to plug 3 in to the original function, so it's 3 minus 3 times 3 minus 4 all over 3 minus 4 times 3 plus 2, which gives me 0 on top over -1 times 5 over -5, which is still just 0. So at 3, 1, 2, 3, I'm at 0. So I'm down here. And then I know at 4 there's a hole, so I'm not going to actually draw it. I'm going to put a hole in the graph. And so now if I plug in 5, I'm going to say 5 minus 3 times 5 minus 4 all over 5 minus 4 times 5 plus 2. And so plugging this in, 5 minus 3 is 2. 2 times 5 minus 4 is 1, so it's 2 on top. And 1 on 1 times, so 2 sevenths, which is just at 5. I'm a little bit above, so it's somewhere like right there. So remember, there's a hole in the graph here at 4, so it's in the positive. So the graph that I get would go something like this. And remember that you're going to find out that it's going to approach the vertical asymptote and the horizontal asymptote as we go to both of those values of x. So there's your sketch of your graph of this function with the hole and everything included. So the next example, we are going to graph this one by hand also, and you'll notice it says keep in mind a slant asymptote. All right, so we talked about before, if the numerator is equal to the denominator, we take the leading coefficients for our horizontal asymptote. If the numerator is smaller than the denominator, the horizontal asymptote is y equals 0. Let me go back and fix this. So the horizontal asymptote up here was horizontal asymptote is y equals the leading coefficients, and that's LC for leading coefficients. And then if the numerator, the top, is bigger than the bottom, we said there was no horizontal asymptote. We said there was none. Well, what happens is when you have the numerator bigger than the denominator, we're talking degrees here. All of these we were talking about degrees. When the degree of the numerator is bigger than the denominator, we actually don't get a horizontal asymptote, we get a slant asymptote. Okay, and so that's what's going to happen here, and we're going to talk about how you get that first of all. So I'm gonna factor the top just to kind of keep an eye on things here and see what we get. I know I'm going to have I know I have a vertical asymptote. Vertical asymptote will be x minus 1 equals 0, so x will equal 1. And so that's where I get my vertical. I get a vertical asymptote at x equals 1. And so if I do that, let's see, so I have that, so I'm going to draw my vertical asymptote in. And then we don't have a horizontal asymptote because the degree of the top is bigger than the degree of the bottom. We're going to have a slant asymptote. And now you're probably wondering how we're going to get that slant asymptote. And this is one of the reasons we learn long division, is we're going to do long division to get the slant asymptote. So I take this, excuse me, and do my long division. And so I say, okay, what do I have to do to make this x look like x squared? I multiply by x, so I get x squared minus x when I distribute. Remember, change the bottom row signs to their opposites, so I get negative, positive. When I add straight down, I get 0. So there's no way I can make the x minus 1 look like negative 2, so it would be a remainder. Negative 2 over x minus 1 would be normally what we talk about. But when we're dealing with slant asymptotes, we don't care about the remainder. We ignore the remainder. And so we only care about what the values of x's are, or any other numbers that go along with it that aren't the remainders. And so I end up with a slant asymptote as y equals x. So it would look something like that. And so there's my slant asymptote that I get for this graph. And that's some pretty good information for us, because just like before, we're going to have graphs that approach from both sides. It may be above, or below, maybe in these little areas, maybe in the big areas. We don't know yet. We just kind of have to work our way around it. We can find x-intercepts and y-intercepts. That's kind of important. So let's set this thing equal to 0 and find the x-intercept. So if I set 0 equal to x squared minus x minus 2 over x minus 1, I'm going to multiply both sides by x minus 1, which will remove the x minus 1. So 0 is really equal to x squared minus x minus 2. And if I factor it, I get 0 equals x minus 2 times x plus 1. And this was the reason we don't have a hole in the graph, is because we had x minus 1 as the denominator. And you'll look that when we factored the top, we didn't have a hole in the graph because we didn't have anything that matched it. So if using my zero product property, x minus 2 equals 0, x plus 1 equals 0. So I get two different places where we cross the x-axis, at 2 and at x equals negative 1. So at x equals 2, we're crossing the x-axis, and x equals negative 1, we're crossing the x-axis. So you could probably see that my graph is probably going to do something like this, above and below in the big areas, not in the small areas, by my x-intercepts. I could try for y-intercepts, and that would be setting all of these guys equal to, setting all my x's equal to 0. So let's see if we have any y-intercepts. So if I say y equals, and in my original function I have, it'll be 0 squared minus 0 minus 2 all over 0 minus 1, you can see that my y-intercept, when x is 0, y is positive 2. So that's actually a pretty good information. I'm going to actually sketch the graph from this, and you can see that I will approach my vertical asymptote, my slant asymptote like that. And then if I want to pick some more points, I could pick some more points and using a t-table to get a little bit more accurate graph. But I know that this graph is going to approach just like this, and because I've already got an x-intercept, and it's got to be in this area down here. It's not going to be in the little areas. So this is the sketch of the graph for this one. This concludes section 2.7a, 7b, excuse me. If you have any questions, please write them down and come to class prepared to ask them. Thank you very much.